This lecture looks at tests of association among variables. Relationships among variables can be thought of as either associations or differences. Previously, I've talked about looking at differences in groups, either differences in distributions across category groups, which the chi-square test examines, or differences in the means or proportions of groups, which t-tests and analysis of variance examined. An alternative is to look at relationships by looking at the associations or the relationships or the shared variance among or between pairs of variables. But with categorical data, nominal measures, association can be assessed with chi-square tests. For example, does household composition relate to brand choice? So you might have several categories of household composition and several brands, and you would be looking to see whether the brand choice, the frequencies across brand choice were associated with the nature of the household composition. With ordinal measures, association can be assessed with Spearman's rank order correlation or chi-square. For example, the question, does social class relate to product expenditures? Where social class is an ordinal measure and product expenditures could be categorized in ordinal categories. With interval or ratio level measures, the tests become more powerful. Association can be assessed with Pearson's product moment correlation, R, or similar techniques such as regression analysis. For example, the question, does income relate to credit card balance? Where income is a ratio scale and credit card balance is also a ratio scale, and we can look at the simple correlation between those. We can include those in regression analyses. We're going to bear in mind as we go through this that we are looking at correlations and need to be careful about inferring causation. Recall from the discussion of experiments, the question of causation is quite demanding and requires that we have control for alternative explanations. And simple correlational analyses don't necessarily imply that control. Now, as I've covered chi-square analysis in a previous lecture, I'm going to move on to Pearson's R product moment correlation. This is the most common statistic that's used in assessing association. Correlation reflects systematic covariation. It assumes continuous interval or ratio measures. And R can range from minus 1.0 to plus 1.0, where minus 1.0 implies perfect correlation, so that a proportionate change in one variable is reflected in exactly the same proportionate change in the other variable, but one is moving upward and the other is moving downward. And positive 1.0 implies that they're both moving the same direction. And in between those, a correlation of 0.0 means that the movement in one variable gives absolutely no information about the movement in the other variable. The equations for R are given here. R XY's correlation between X and Y is given as the standard deviation of the XY divided by the square root of the standard deviation of X times the standard deviation of Y. And then you see the expanded versions. And you can look at these and see that the sign of R comes from the numerator, which is the covariation factor. And the size of R comes predominantly from the denominator, which reflects the variances of X and Y. So whether a deviation from X in a positive direction is associated with a deviation in Y, also in a positive direction, determines the sign. Higher covariation and lower variances increase R. These are some figures to illustrate correlations. You see in the top left a correlation of positive 0.95. So this is a scattergram that is nearly a linear relationship. And as we move out on the x-axis, we're moving steadily up on the y-axis. And the middle top shows a positive correlation of 0.6. Here the scattergram is slightly more spread out, but in each case as we move out on X, well, not quite all. In most cases as we move out on X, we're also moving up on Y. And then C, a perfect correlation, those lines fall on an exactly linear relations. They fall exactly on the same line. And in the middle we have negative correlations. So the first one, negative correlation 0.60. As you move out on X, you're moving down on the y-axis. And then with a negative correlation of 0.4, we see the scattergram is slightly wider. There's still some information content. As you move out on X, you tend to move down on Y. And then finally a perfect negative correlation. And on the bottom row, various possibilities for zero correlations. There are an infinite number of zero correlations. So all of these, you can see that changing value on X doesn't necessarily tell you what's going to happen on Y. In fact, it doesn't tell you anything about what's happening on Y. When researchers are investigating shared variance among pairs of variables, they typically look at more than one pair. So they're typically looking at a number of variables to try to determine which pairs of the variables share variance. And the result of that is a correlation matrix. This is a matrix with the same variables as rows and columns. And the cell entries represent inter-item correlations. So each cell entry is the R value for the correlation between the designated row and column variables. Now, of course, the diagonals of a correlation matrix are 1.0 because they represent the correlation of a variable with itself. These correlation matrices are a useful way to investigate large data sets for possible associations. One of the common applications of correlational analysis is to discover relationships that weren't anticipated. So correlation statistic can be used to test an hypothesized relationship, but it can also be used to identify an unexpected or unanticipated relationship. Another common application is to test the reliability of composite scales. A composite scale is a scale that is comprised of separate measures. It's common, as we've seen, to assess attitude toward a brand with 3 or more items. A question such as how good or bad do you find this brand? How desirable or undesirable do you find this brand? how attractive or unattractive do you find this brand, and there are other possibilities. So if you're asking, if one is asking several questions with the intention to take the average score or the sum score on those questions as the indicator of attitude, then it makes sense to assess the reliability of that, and a scale would be highly reliable if each of the items tended to be correlated with the other items. So here we see an example correlation matrix. These represent data from a number of firms looking at their sales, total sales, looking at their advertising, how much money they spent on advertising, looking at product quality. This is a measure of perceived product quality relative to competing brands, and looking at price. And again, this is relative price relative to other brands. You'll see that you've got the same variables in the rows as in the columns, and therefore the diagonal values are 1.0, representing the perfect correlation of sales with sales and advertising with advertising. And then the off-diagonal entries, and typically a correlation matrix you see only the bottom half, because the correlation of advertising with sales, 0.25, is going to be exactly the same as the correlation of sales with advertising. So given these, we can look at these correlations and ask whether they make sense. One of the first questions is whether this is a sensible or expected sign for each correlation. So we see that advertising is positively correlated with sales, and marketers should take heart from this finding. Increasing promotion does help drive sales. Also see that product quality is associated with sales, which is also a good sign, certainly for engineers who invest a lot in trying to make higher quality products. And that price is negatively associated with sales. So that's the first column, and that reflects simple economics. In the next column, we look at some subtler relationships. Quality and advertising have a near zero relationship, which suggests that firms that have higher quality products are not advertising any more or less than firms that have lower quality products. Offhand, I don't have any explanation for that. I'm not sure we would expect that higher quality products would advertise more. They're certainly advertising differently. They're positioning themselves differently, but the amount they spend on advertising is neither more nor less. Price shows a negative correlation with advertising, suggesting that lower priced products advertise slightly less than higher priced products. I don't know whether that is sensible. Perhaps lower priced products, firms with lower priced products may include firms that are struggling and are engaged in price competition in order to stay afloat, and they may have less budget for advertising. But clearly there are successful low-price competitors that appear to advertise quite a bit. Walmart comes to mind. And then in the next column over, the last entry is the highly positive correlation between price and quality, 0.65, which makes sense. You would expect that perceptions of quality are driven by some objective quality, and that objective quality reflects higher costs of inputs, either better materials or better workmanship. and that, of course, translates into a higher price in the marketplace.